Alright, so in this video is going to look at the section on stationary waves, the materials, and then finally on the practical double slit and diffraction grating type stuff towards the end. So let's first start with this 6 marker about stationary waves. Now I think it's really important to reiterate at this point that a lot of people kind of treat these 6 markers a bit like a mind dump and just write everything they know about stationary waves down, and so get generally not very good scores. So for these questions you need to write very well thought out, well planned answers, or you're not going to be getting into the top level for these questions. So what I've done is I've gone through, I've highlighted what I've written in which section it's relevant to. So pink is when I'm explaining how a stationary wave is formed, yellow when I'm describing features of a stationary wave, and then green describing the processes that actually make those features. So to start off with, we're going to look at actually how you go about making a stationary wave. So the key thing is it's formed from 2 progressive waves. They have to be traveling in opposite directions at the same speed and have the same frequency, and they need to meet or superpose in a certain location. So there's many scenarios in which you can have 2 things traveling in opposite directions at the same speed and frequency, but will never meet because they're traveling like parallel to each other. So it's important that you illustrate actually these waves need to meet. Okay, so that's how you actually form a stationary wave. So then we're going to start thinking about features. So in terms of the features, one of the things you get is something called an antinode, or a region of maximum displacement. And the reason you get that is because the 2 waves traveling opposite directions meet in phase, or have a phase difference of 0. And that causes constructive interference to occur, which is why you get the large maximum displacement. You also get these regions called nodes, where there's a region of 0 displacement. And that's where they meet in antiphase. So not that they are out of phase, that they meet in antiphase, or 180 degrees phase difference, which causes destructive interference to occur. So the conditions are very specific for forming nodes and antinodes. Okay, and then the last feature of a stationary wave is that they don't transfer energy from one location to another, and that's because the 2 progressive waves are traveling at the same speed in opposite directions. So essentially, as one moves energy one way, the other one moves that same amount of energy the other way, and you get 0 energy transfer overall. So that's actually all you need to answer this question. So you can see I didn't get anywhere near using the amount of space allowed for this question, and generally you don't need to. So for these 6 mark questions, it's about having a few very clear, very thoughtfully planned out statements, and that's how you end up getting 6 out of 6. If you just dump everything on a page, if a single thing you wrote on the page is wrong, that means your answer gets capped at 2 marks. So you need to be really careful with these. Okay, so that's just stationary waves. Okay, so now we're going to look at the question on the mechanical properties of materials. So I have to look at this bit out of order because this app doesn't let me sort of flick back from other pages. So the last part of this question asks to draw a material that undergoes brittle fracture at 176 but has a higher Young's modulus. So that's what this will look like. So this is what the graph I've labeled F is on here. So it's brittle fracture, so essentially you've got 0 region of plastic deformation, and it's got a higher Young modulus, so that's why it's got a steeper gradient, because Young modulus is the gradient of this graph. Also, in terms of doing the work done section, you can see here my method for figuring out the energy it takes. You can see I've broken down this graph into a triangle, a rectangle, and then used a counting squares method to determine essentially the total area underneath it. A lot of people with this area question underestimated too much. Essentially, they cut off way too much of this graph and got an estimate that was below the lowest value. So you need to make sure you're being as accurate as possible with your counting squares, using a counting squares method when doing an area here. Okay, so those parts. So let's have a look at these original parts. So to find tensile strain, strain is the ratio of extension to its original length, or extension divided by the original length. It's tensile strain, so it's a strain caused by a tensile stress or a stretching force. That's what tensile means. Okay, then state the breaking stress of copper wire. So it's where it fractures. So you can see it's indicated where the fracture is. They were really nice to you. They said, here it is. You can see that's about 1.9 times 10 to the 8. If you look on this axis, you can see it gives you the power of 10 here. So you need to make sure you have that in your answer. Okay, and then mark a point on the line where you consider plastic deformation may have started. So you could have gone from anywhere where it became a non-directly proportional graph. So about, let's see, you could have gone from anywhere from here up until I think we allowed somewhere sort of up here. That would be where your plastic deformation starts. This is where you're getting a rapid change in gradient of your graph there. Okay, and then use your graph to calculate the Young modulus. So, because it says use the graph, that's telling you should be using the gradient of your graph, which is the Young modulus, and you should be using as long a section of the straight line section as you can. So that's what you can see from the values I have picked. And if you did both of those things, you should end up with an answer of this, or it could be a 1.2 times 10 to 11 pascals. They're the same thing there, but it's really essential you use the gradient and you show that you are using the gradient on your graph. Okay, so this is what I was talking about earlier in terms of using the area under the stress strain graph to then work out the work done per unit volume in this case. So you can see, as I said before, I divided it up into a triangle, a rectangle, and then essentially I worked out the number of squares I had underneath the original graph. That was my method of doing it, and I came in at sort of the top end of the estimate, so I slightly overestimated it but was close enough that I was in the range. So that's the method you use. Again, as I said earlier, lots of you just tried to simplify it too much and you came too far under the value accepted range, so you need to be very precise. And then to work out the actual work done, if you've got the work done per unit volume, you need to multiply that by the volume. So you need to use your density equation, rearrange to calculate volume. Loads of people couldn't rearrange this very basic equation, which was very disappointing to see. Once you've got the volume, you multiply your answer by that, and you end up with something around this. And again, there was a range depending on what you got here. So this last part I talked about earlier. So high Young modulus, steeper gradient, brittle fracture means there's no plastic deformation section. It just breaks at the end of the linear section there. Okay. And then finally onto the practical question looking at diffraction gratings, as you've just done this practical. First one should be very straightforward. So percentage uncertainty, you've just got a value, so the uncertainty is going to be the precision of this value. So you can see that that's 0.1 times 10 to the 3. The value you've got here times 100. You'll notice I got rid of the 10 to the 3 because they'll be on top and bottom line, so they're not necessary. If you do that correctly, you should get 2.9, giving it to two significant figures because it's percentage uncertainty. Okay, then determining the diffraction grating spacing, that's just 1 over the number of lines per meter. So that gives you a spacing in meters, and then to turn it into millimeters, you times it by 1,000. Again, lots of people really didn't think about this, and when having got this then divided by 1,000, you should know better than that by now, really. And then determine the absolute uncertainty in the value of the spacing. We've got the percentage uncertainty, we've got the value, so now we can essentially work out what the absolute uncertainty is. So the thing to realize here is we know the percentage uncertainty in n. This is just an integer, so that has 0% percentage uncertainty, so that gives you the percentage uncertainty in d and n will be the same. So that's how we were able to get a percentage uncertainty here. And then we've got a value as well from the previous part, so putting those two together would give you a value of 0.0082 millimeters. For some reason in this question they did allow you to round this to one significant figure and give 0.01. I was quite unhappy about that because that then meant you could just get away with guessing. I was not happy with the mark scheme about this. This is what you should be doing for this question. Okay, so then we've got this is then put into an experiment. So the diffraction grating is put 2.5 meters from the screen. That's what you can see this distance here. And we've got this interference pattern produced, and we've been given the wavelength, which we'll use later on. So you need to measure what your spacing is. So you should know, thinking about your percentage uncertainty, you should measure as big a distance as you can. So that's what you can see on the diagram. I've measured from here to here because you want to measure as long as you can, because that minimizes your percentage uncertainty. And then having done that, convert that into what one spacing represents there. So that's what you should have done. If you did anything other than that, or measured smaller distances, you would have lost the marks for this one here. Then calculate the number of lines per meter on the grating. This was very depressing to mark because for some reason people just flipped over 5.2 millimeters and gave that as their answer. No. So first of all, what you need to do is work out what the slit spacing is. So you've been given enough information to do that. So because you know the distance to the screen is 2.5 meters and the distance between fringes is 5.2, this would therefore be your first order over here. So what you can do is work out what sine theta is for this one, and then put it into your diffraction grating equation. N lambda is d sine theta, which, as you can see I'm doing here, gives you what d is, and then n would be 1 over d. So that's what you can see happen in the final stage there. So that's the approach to solving this question, and if you just flipped over this number, you haven't thought about it at all, and that's not really good enough. And then the final part, these two were not done very well at all. So in terms of working out whether or not your answers agree, you need to look at the percentage difference between the value calculated and the stated value, which is what you can see I've done here, 5.7%. And so, but your percentage uncertainty is only 2.9%. So actually the value calculated and the value stated are not within the uncertainty limit. So they are not within agreement of each other. So that's how you would explain whether it's valid or not. Any other comment is not like, oh, they're quite close or they're not close. It's just not valid. You need to think about the uncertainty. And then this last part, I read lots of ridiculous things here. So state one safety precaution, and lots of people wrote, don't shine it in people's eyes. Well, of course you're not going to shine it in people's eyes. You'll go around trying to blind people? No, what you do is actually set up the laser pointed away from any areas people's eyes are going to be, so pointed at a wall or fixed way below eye level, those kind of things. You are not going to be waving lasers in people's eyes, and you should not have to say that. That's not a valid safety precaution there.